exam graded by today, but there are a lot of exams. So my target's next Thursday. Go through a couple of announcements. So let me be clear on the exam 1 corrections. The corrections have been graded, but I haven't incorporated it yet, and I got to take time to make sure that's done correctly because the exam was out of 100 points, but the corrections were out of 25 points. So I want to make sure, as I said, the final exam grade is going to be the average of what you did on the exam and what you did on the corrections. So if you got a 25 out of 25 on the corrections, that's 100. So I just want to make sure that's done correctly. So I will get that done probably today. That's something to be excited about. Homework is graded. Homework 8.1 is due today. Hopefully you found that homework 8.1 was easy, I hope. I think homework 8.2, the formulas are even easier. There's a little bit more drawing necessary for 8.2, but I think it's even more straightforward of an assignment. And so today what we're going to do is we're going to continue our discussion of the analysis of stress, and we're going to yield a very fundamentally straightforward technique for assessing stress transformations, and this is Mohr's circle. Now, first off, make sure that we are all clear on this. So the idea is that if I am given a stress state and I need to determine a new stress state based on some angle of orientation, theta, I can basically plug in a box, which is essentially just taking our initial stress state and doing some trig to it. I mean, the formulas are a little nastier than just taking the stress and multiplying it by the sine, multiplying it by the cosine, whatnot, because we have to ensure that both this stress state and this stress state achieve equilibrium. So, there's a little bit more to do, but in the end, it's some plug and chug trig. Okay? Does everybody kind of understand both the formulas and that concept? Everybody kind of get that idea? Okay. So if you understand that, our discussion and extend it one step forward, okay? And there's a very natural question, which is, if I have this stress state and I can rotate it to get a new stress state, maybe the question is, what's the worst way to rotate it? What's the worst case orientation? What's the worst angle at which I should swing my samurai sword or lightsaber? Because is along that orientation that I as an engineer am interested in, because it is those stresses that I would like to design for. Okay? We have a name for those stresses. We call those principal stresses. And so what we need to do is first discuss principal orientation as well as the maximum normal stresses. The maximum normal stresses are specifically the principal stresses, but then there is also a maximum shear stress that we could get as well. Now, I want to go back to the plot that we discussed last time, and I want to really hone in on here. So, if you remember the problem that we had last time that we did in class, I gave you a stress state of, it was like 6 KSI, negative 10 KSI, and then negative 5 KSI. So these were the two normal stresses right here, 6, negative 10, and then this dotted line represented the shear stress. And so I gave you the initial values, and then as we rotated it, we got new values, right? And I think what we did in class is we found the stresses along, I think it was something like right here, right? It's like a 53-degree angle, and so we got new values. It was something like that. I probably have my line drawn off a little bit, but you kind of get the idea. Now, what I want to focus on is what's going on at this green line, because there's a lot more going on than you would think, okay? So, but let's just sort of investigate the graph, okay? When we look at the graph, what we find is that there's some magic in that green line. Simultaneously, we find that there is zero shear stress. So at the location of zero shear stress, worst case normal stresses. And so a very important question is this always the case? And I will go ahead and tell you the answer is yes, okay? And there's actually a very easy mathematical way to show that. I'm going to show you that here in a little bit, okay? But there's also something else that's worth mentioning, is that if we take this line and we shift it 45 degrees over, we're right here, and we find something else that's kind of magic going on. We find that 45 degrees away, we have maximum shear stress, but we also have normal stresses that are equal to one another. Okay? I think in the last lecture I said 90 degrees. I think that I misstated that. But then again, if you remember, a lot of our stress transformations involve 2 theta. So that's, I think, why I said that. But is everybody sort of with me so far on these sort of general observations? Okay. So let's first off, let's try and see if this is always the case. Okay? All right. So one way to determine the worst case orientation is to use calculus. Okay? My normal stress is maximized, I'll just take the derivative, set it equal to 0, and solve for theta, right? So this right here is the expression in that big old yellow box for sigma 1. So this tells me what sigma 1 is given some stress orientation. So if I take the derivative of this with respect to theta, because I'm trying to figure out the worst case angle, what do I get? Okay, well I get the derivative of this. If I'm taking the derivative with respect to theta, that's a constant, so that's 0. Okay? Okay, what about this right here? Well, what's the derivative of the cosine? It's the negative sign, but then I got my lovely friend the chain rule, right? So 2 theta, I take the derivative on the inside and I get 2. That's why the fraction goes away. Same thing what's going on over here. I have tau xy times the derivative of the sine. The derivative of the sine is the cosine, but then I got my chain rule friend here. So that's why I have that 2 sticking out here on the outside, right? Everybody sort of with me how I went from here to here? Take this, set it equal to 0, right? And solve. So what I'll do is I'll get all this stuff over on one side. What I have here, divide both sides by the cosine, divide both sides. Inverse tangent multiplied by a half. I mean, I'm doing that kind of quickly, but ultimately it should be some pretty straightforward algebra. Everybody sort of with me on that? So that's one way of finding the worst case orientation, but another way is to assume that whenever this is maximized, equal to 0 and see what happens. And when I set this equal to 0, right? Lump it on one side of the equation, solve for theta, and it's funny how I get the same thing. I get the same thing in this gray box as I do in this gray box. So the question of, at the location of 0 shear stress, we find worst case normal stress. Is always the case? Yes, because if I look at the derivative, set it equal to 0, solve for the angle, or I just set the shear stresses directly equal to 0, solve for the angle, I get the same angle. So that's always the case. And so that's an incredibly powerful observation that we can use to develop this graphical technique called Mohr's circle. Okay, with me so far? Now, what ends up happening is so think about this from a calculus perspective. How do I determine a maximum? Well, I have a function, take the derivative, set it equal to 0, solve for x, in this case theta, then take that magic value of x, plug it into the original function, that's my maximum, right? That's Calc 1 in a nutshell, right? So what I'll do is I'll take this expression here for theta, plug it into my big yellow box right here, and do a bunch of simplification, and I arrive at this, okay? Now I'm more than happy to show you that algebra if you want. It's not hard, it's just a lot of messy algebra and trig to get from here to here. But what we get are these 2 very magical formulas here called sigma 2. And I propose to you that under a generic stress orientation, these are the worst case normal stresses that you could ever get. In fact, if you look at the formulas are exactly the same, except for one's a plus and one's a minus. So it is very common to collect those into a single equation. Right here is the expression for normal stresses, or for principal normal stresses. Okay? And if you look at it, a lot of times what we will end up doing, okay, and you'll see this here in a little bit, is we say sigma 1, 2 equals, and so we have a term here plus and minus this. So the first term we end up calling sigma average, which, I mean, look at it. We have sigma x plus sigma y over 2. That's just the average of the normal stresses. And then plus and minus something. And let's take a look at what's inside this expression. We have a all under a square root. Does that calculation look kind of familiar? Like a pile of junk squared plus a pile of junk squared, take the square root. Doesn't that kind of look like a Pythagorean theorem? Right? If I was solving for the hypotenuse of a triangle. Like if I had a right triangle in it and I had leg 1 and leg 2, I would take that leg squared plus that leg squared, take the square root. Right? So it's the same thing here, but if you remember, trig is the study of circles, as I mentioned last time. I propose that this term under the second square root is the radius. It is the radius of Mohr's circle, and you're going to see why here in a second. So a lot of times you'll see me write this as this, and this is one of the reasons why determined analytically. Okay, everybody with me so far? Mohr's circle. I am curious, has anybody seen Mohr's circle in another class before? Like, have you seen it in some of your mechanical classes or maybe even civil classes? It's possible you haven't yet. If you haven't, I guarantee you that you will. It is one of those tools and tasks that it's just sort of seminal that every engineering student is expected to sort of know how to do this. It's like Bernoulli's equation, or being able to take a derivative, or being able to draw a shear and moment diagram. Mohr's circle is very fundamental to the skills necessary for engineering. And if you haven't seen it yet, I guarantee you will see it again. It is an incredibly powerful and simple graphical technique for doing a lot of those stress transformations. And where it's based on is this. If you remember, there are 3 ideas that sort of get linked. First is just the development of our sine, cosine, tangent functions to try and solve a triangle. Then we start looking at the graphs and we say, well, they're periodic, they're waves, we can take the derivative of one and get the other. But then, if we really start plotting them on a circular plane, we find that the sine and cosine functions are really just x and y coordinates on a unit circle. And so we can use this kind of analogy to sort of figure out, can we make this a lot simpler from a mathematics standpoint? And the answer is yes. Okay. Now I'm gonna bring it back. This is probably Math 132 for you, right? Or maybe pre-calculus in high school or something like that. Remember the equation for a circle, right? We have the quantity x minus h squared plus the quantity y minus k squared equals r squared. Has everybody seen this before? That this is the standard equation for the plot of a circle. And so we are able to achieve the plot by recognizing that the radius of the circle equals r and the center of the circle equals h comma k. Okay? Now, what we're going to do is we're going to look at our equations for stress transformations, but we rearrange them a little bit. So this is the sigma 1 and tau 1, 2 equation in that big old yellow box, but I've just rearranged it a little bit. I've moved this over here, this one term over here. Now, we're only looking at one of the normal stress equations because sigma 1 and sigma 2, they're kind of the same equation, just shifted, 90 degrees. So they're not as independent. Like you could argue sine and cosine really aren't that independent because you can take sine, shift it, and boom, you get the cosine. A little bit of alphabet soup coming in the next couple slides. Don't worry, I'm not going to make you redo it, but just bear with me. What I'm going to do is I'm going to take these equations and I'm going to square it, okay? Now, in order to square these, what I got to do is I got to break out my friend foiling, first outside, inside, last, right? So I'm taking this normal stress equation, the shear stress expression, squaring it. I'm not making you do it, don't worry. I'm just having to go through this and I'm doing some foiling. Then what I'm going to do is I'm going to take these expressions and I'm going to add them to one another. Now, if you follow the math, what you find is that there is a lot of stuff that cancels. Like if I take this term and add it to this term, all this stuff in red is going to cancel because it's all the same. What you find is that I'm adding a cosine squared plus a sine squared. What is the sine squared plus the cosine squared? 1, right? So a lot of this super nasty trig just washes away. And what I'm left with is this. And if I look at this and I compare it to the equation of a circle, squared, y minus k squared, r squared. I look at this and I say, okay, this is the center, this is the radius. Okay, so that's it. That basically what we're doing is taking all of the stress transformation expressions that we've derived and making it super simple. Plot of our stress transformations on a circular range. And we call that circular plot Mohr circle. Okay, so here's how Mohr circle works. Okay, if you want to plot Mohr circle, it's this simple. Okay, so you're gonna be given a stressed state. So the first thing to do is to compute the average stress. Okay, the average stress, sigma x plus sigma y over 2, go back to what we did before in this previous slide. That's the center of the circle, right? So this is where the center of the circle is, and it serves as the center along the x-axis. The radius is just what was left over on the other end of that expression. This squared plus this squared, take the square root. Boom, Mohr circle. And so what this tells us is that any point along the circle corresponds to stress state under a given rotation. So instead of form a single stress transformation, so like what we did on homework 8.1, I gave you a stress state. I said, what's the new stress state if the angle is 20 degrees, right? Well, if I give you a stress state, this is the result of all orientations, right? So this isn't just theta equals 20 degrees. This is all thetas, all in one. Minus the radius, these two values right here are the absolute extreme normal stresses. This value and this value are your principal stresses. The x-axis is plotting along normal stresses. The y-axis is plotting shear stresses. So what's the absolute maximum shear stress that we see? It's just the radius. So with a very, very contained set of expressions and a very simple plot, I can tell you worst case normal stresses, worst case shear stresses, all at once. Very, very simple, okay? Let me go through some observations about Mohr circle. So again, and this is a lot is what I just said in the previous slide. So by investigating the plot, we can look at it, we can find that the radius of Mohr circle is the worst case maximum shear stress. And the principal stresses, the worst case normal stresses, are just sigma plus r, sigma average minus r. Now, what you can also do is go back to, let's say, an original stress state by rotating 2p clockwise. And what here is maybe a little fuzzy to understand textually. You'll understand it very well when we do the problem here in a second. But basically, you can take your principal stresses and undo that rotation and go back to the original stress state. And again, this will all become clear with an example. Speaking of, let's look at an example. So this was dealt with in our previous problem. Okay? What I want to do is I want to determine the worst case orientation, and I want to draw a Mohr circle. And you will see just how easy this really is. Okay? So bear with me. Let me pull this up. And I want to mention one thing. Recall from previous example, sigma 1 is negative 9.04. Sigma 2 is plus 5.04, and tau 1, 2 is negative 6.28. That's what we got in the last example. What I will tell you is that if we were, let's take a look at some of these values. What we found is that, let's sort of think about this a little bit. If we go from here to here, I think that at a minimum, the need for a stress rotation becomes very clear. For example, if I just looked at these values, I'd be designing 5 KSI. However, under some rotation, it's negative 6.28 KSI. So if I design for this, but this tells me that there's an angle at which the stresses are higher, that's a problem, right? I want to be designing for the worst case stresses. So at a minimum, going from here to here should just be numerical. If we rotate our orientation, our angle, if we change the orientation of our section cut, we get higher stresses, right? We go from plus 6 to negative 9 and so on and so forth. So now what we're going to do is figure out, okay, what's the worst case orientation? And I think you'll find that the math is pretty easy. Okay, so again, we have sigma x is plus 6, sigma y negative 10, tau xy, keep her coming up, is negative 5. Okay. So the first thing that we're going to do is we're going to figure worst case orientation. So principal orientation. All right. Now, our expression for that is pretty easy. It's 1/2 inverse tangent of better than that. And pretty easy formula to remember. So 1/2 then we have 6 KSI minus negative 10 KSI. So I'm not gonna skip on the signs. I'm not gonna go, oh well, this minus this is positive. I'm gonna be diligent and use my parentheses. Now what are we getting for this? By the way, let's do this in degrees. And to be clear, it will come out as negative. That's okay. Anybody have an answer for me on their Casio FX 115 ES Plus or similar scientific calculator? And it's got a decimal to it like 003, right? Like it's something like that, right? So just so you know, and you'll see where this is going to come in. Do you agree with that? In order to, so what we're going to do is we're going to compute actually, no. Compute principal stresses. We're really not going to use this angle, but you're going to see where this angle pops up here in a second. Okay, so just bear with me. That angle actually isn't going to help us in computing the normal stress or the principal stresses, but we'll see where it's useful. Okay, so our expression that we derived is that sigma 1, 2, and so we tend to use Roman numerals to differentiate it from the 1 and 2. So our expression is sigma x plus sigma y over 2 plus and minus the square root of plus that. And to me, I find this is a really easy formula to memorize. We sort of have like our sigma average plus or minus a root, and then we have shear stress squared, and it's basically the same term, only minus. So I think it's pretty easy to memorize. So sigma 1, Roman numeral 1 that is sigma x plus sigma y over 2 plus. So honestly, it doesn't really matter which one you call sigma 1, sigma 2, but it is traditional that sigma 1 is the term that's plus and sigma 2 is the term that's minus. That's traditionally what we use. So this equals, I got an answer?
7.434.
Do I have a second on that? Okay. Now, I'm lazy, so we're going to see if this works. So the only thing that changes from sigma 2 is that this term becomes a minus. So you might be able to pull that out of your calculator and go, okay, what if I just change this plus to a minus? What do I get? There we go. Okay, so I propose those are the maximum normal stresses, okay? Are those values bigger than what we got last time, 7 and minus 11? Well, last time, plus 5. This is the highest, 7.434 is the highest possible positive stress, and negative 11 is the highest possible negative stress. We cannot find a rotation that will give us a normal stress bigger than these two values. Although that becomes abundantly clear when you actually plot Mohr's circle. And so let me show you how Mohr's circle works. Okay? So the first thing we plot, or we compute, is the center. And the center is sigma average, which is sigma x plus sigma y over 2, right? Which is, and this is some really cool stuff to see here, by the way. So 6 KSI plus minus 10 KSI over 2. What do we get for this? Yes. So is the average of your normal stresses. And the average of your normal stresses is -2. What about the average of these two? What's the average of these two? What do you get? This and this, -4, divided by 2, -2. What about what we got in our last example? -2. It doesn't matter what normal stresses you use. As long as they correspond to a given rotation, the center of Mohr's circle will always be in the same spot. So, just saying. All right. The radius is sigma x minus sigma y over 2 squared plus tau xy squared is the following. So what do we get for this? I got a second on that? Here's the crazy thing. Again, if you were to take here, the negative 9.04, the plus 5.04, the negative 28, plug them into this expression, you will get the same radius. The radius of Mohr's circle and the center of Mohr's circle does not care about a given orientation because these values are reflective of all orientations. Try it out. With me so far? All right. Okay, now we're going to try and be fancy here. Let me see. So, hold on. Let's see. Oh. Is it like that? Okay, it's like that. Shapes. Okay. We're actually going to be fancy with this. Okay. Okay. Let's make this a little longer. Do that over about like that. Okay. So what we're doing when we're plotting is we're plotting normal stress on this axis, shear stress on this axis. Okay. Now what did we find? We found the center was -2, radius, whoa, what happened there? Radius is 9.434, Notice the radius formula will always yield a positive answer because you can't have a circle with a negative radius. Okay? And let's see what we get. Okay. I'm actually going to draw my circle down here to get it right. I think that looks something, let's see, about like that. Is that about right? So maybe I'll shift this over a little bit. About like that. Is that about right? Maybe I'll shift that just a little bit. I think that's about the best I'm going to get it. Okay? So, let's see. So, that is the center of Mohr's circle. And so, we're going to say that's -2, 0. Right? And we're going to say that Mohr's circle has a radius of 9.4. Actually, hold on. 9.434. Okay. Does that make sense? All right. So, actually, let me move this point description right here. Let me move this like right there. Okay. Now, the maximum normal stresses. So where are the biggest values that we find on this circle on the x-axis? Well, it's right here and right here. So this is sigma 1, this is sigma 2. And how do I find sigma 1? I take the center plus the radius. And I find sigma 2 by taking the center minus the radius. And notice how the plot shows you pretty easily that there are no rotations, that there are no normal stresses bigger than those two. Sense? Now, what about shear stress? Okay? What is maximum shear stress? Well, the maximum shear stress is that value. It's R, right? So tau max and if you want, you could say plus or minus. Down here. But the other interesting thing is, here's something that's kind of interesting about the x and y coordinates of this point and the x and y coordinates of that point. So the x and y coordinates of this point, x and y coordinates of that point. Would the x coordinates be the same? Aren't the x coordinates the normal stresses? Seems to me, I seem to remember this trig plot in our notes that said that when the shear stress is maximum, the two normal stresses would be equal. It's almost like this circular plot is telling me that on the top and bottom of this circle, we're getting maximum shear stresses, but the normal stresses are equal. You know what else is kind of crazy? That plot that we're seeing is for this actual stress rate, this numerical example. And it's funny how when the shear stress is maximum, the normal stresses are negative. And I don't know about you, but when the shear stresses are maximum, the x-coordinates of these 2 points are negative. It's kind of crazy, isn't it? In this, I want to show you something else, but I want to stop for a second and see if this all makes sense. I want to show you something. In the beginning, the whole purpose of performing a stress transformation is to recognize that while we typically do the analysis according to a chosen coordinate system to make our lives easier as analysts, in the end, that orientation is arbitrary. What matters is this. What matters is what's the worst case orientation. To show you something, watch this. Take this circle, and I'm going to rotate at a clockwise angle down here. Let's do the same thing up here. Now, how much of 32.006 degrees. Now, why 32.006 degrees? Why that? For that angle showing up right here. Rotating clockwise because the angle is negative. Remember in trig that positive angles are counterclockwise? Clockwise angles are negative. So the question might be, what are the coordinates of these points? Coordinates of those points? Down, they should be equal, right? What if I told you that the y coordinates were -5 and +5? If you don't believe me, you can do the trig and see. But what can you tell me? Now let's talk about the x coordinates. Would you agree that this x coordinate is positive, this y coordinate is negative? Maybe it's 6 and -10. I seem to remember that we were given an initial stress state of this. And that is just one of an infinite number of stress states along a given orientation. In the end, though, looking at this, it's arbitrary. It's just a random stress state on the circle. What really matters is this and this, and that. Now, to be clear, if I have a bar, and I want to be crystal clear, if I have a bar and I'm just yanking, draw a Mohr circle for just a single stress state, for just a single stress, it's not going to tell me anything. It's just going to tell me that the worst case stress is the normal stress. Multiple stresses applied all at once. It is only when you have situations of what I would call combined loading that Mohr circle becomes a necessary tool for the purposes of analysis and design. Does that make sense? Here's what we're going to do next time. I'm going to give you a full, palpable, sink your teeth into examples of combined loading. A couple scenarios where it's not so simple, okay? We're going to be able to use all of the formulas that we've been deriving all semester and combine it with this, and you'll see, okay, I finally get it. Because I would imagine even now, this is a little abstract, because it's like, okay, you've got this stress state and this sigma x, sigma y. Where the heck did that come from? You'll be able to understand where that comes from and how to apply everything come our lecture on Thursday. What we're then going to do is we're going to look at a couple of different special cases. So one of the things we're going to look at for you mechanical engineers is the analysis and handling of a thin-walled pressure vessel, which is something you mechanicals need to deal with. And then if we have time, we'll maybe do something 3D, but it won't be like super fancy software related. It'll just be a little bit more practical. And then we'll get into buckling a little bit later. And then for the most part, we're sort of winding the class down. So, okay, let me stop for a second, see if anybody has any questions on this. You'd like it if I let you go 30 minutes early.
I'd probably give you a firm handshake.
I'll give you a break in time for dynamics. That's all I have, everybody. I'll see you all on Thursday.